Good afternoon, everyone, and welcome to the launch of our Spring 2023 series of Quantum Thursdays, hosted by Co-Design Center for Quantum Advantage. My name is Kimberly McGuire. I am the Chief Operations Officer for C2QA, and I'm so excited to launch this series for the spring. We've got 8 exciting talks lined up starting today. With the first one that you see, Yuan Liu, I'm going to introduce our moderator for this spring series, none other than Raymond Samuel. Dr. Raymond Samuel is a professor at North Carolina A&T State University. He is also the lead principal investigator for C2QA's affiliate partner, which is also NCA&T, and we're just so happy that Dr. Samuel can join us on today. So without further ado, Dr. Samuel, you have the floor.
Good afternoon. Thank you, Kimberly. We're really excited to be here. We at North Carolina A&T are excited to be part of the C2QA family. And we have been actively engaging undergraduates and faculty in the QIAC ecosystem, and really excited to be a part of this program. Without much further ado, I'd like to introduce our speaker for today. Yuan Liu is a postdoctoral scholar at MIT's Department of Physics, and where he's working in quantum computing, particularly quantum chemistry. And here with him is his advisor, Professor Troy Van Hoos. I probably messed up the name. Okay. Who will do a brief introduction of Yuan for us to get started. Troy?
Thanks, Raymond. Yeah, it's my pleasure to introduce Yuan. I think he'll tell you a little bit about his background. I can briefly say that his background is both in physics and in chemistry. So he did his PhD at Brown, working with Brenda Rubinstein, who's a chemist, and Lai-Sheng Wang, who's for molecular physics kind of person. And yeah, as his talk will show you, he's interested in that interface between quantum computers and applications to chemistry, which is, people have talked about chemistry as being "quote unquote" the killer app of quantum computers, and as one of the things that quantum computers will, in the near term, be able to transform. And he's really working on trying to understand, what are the technologies? How does quantum computing shift paradigms in chemistry? And he's also working on some other quantum computing algorithms, but I think that's what he's going to talk to you about today. So I'm really excited to hear him speak. And I'll turn the floor over to you, Yuan.
Great. Thanks, Ray and Troy, for the nice introduction, and thank Kim and Donna for the invitation. It's really a great pleasure to be here to tell you a little bit about, some of the research and my career trajectories, how I got into quantum. So let me start okay, so here's an outline. So first to talk about my somewhat, convoluted trajectory into quantum. And then I will, in the second part of the talk, I will focus a little bit more on the research side of give you some general background of chemistry and chemical physics, and then talk about how quantum computers and algorithms can be helpful. And then I will present a recent research effort on leveraging small quantum computers to solve large electronic structure problems in the framework of embedding. So I will then summarize and give you some, outlook. My academic career really just start from undergrad, where I was physics major undergrad at Tsinghua University back in Beijing. So as undergrad, I do some kind of research on AMO physics and a little bit of quantum chemistry. So this is the main part of the campus of Tsinghua, and I spend a lot of time in this building, study physics. That's study room there. So my undergrad advisor is experimental AMO physicist. So he worked a lot on photoelectron spectroscopy, and I end up doing a little bit of experiment, with him at the beginning. And then for my undergrad thesis, I did some theoretical work on calculation of, photoelectron angular distributions. As you can see, is more of a AMO physics style. And there is a theoretical chemist professor in the chemistry department of Tsinghua University, where I learned a lot about starting to learn about quantum chemistry, especially electronic structure with him. So those are my early days that I beginning to learn a little bit about quantum. So after undergrad, then I came to the USA to study PhD in chemistry department. So I started as in my first year doing physical chemistry experimentalist as an experimentalist on photoelectron spectroscopy. So these are a typical PChem lab with Professor Lasheng Wang. And so to give you some idea, these are the laboratories, how the laboratory look like. There is the giant laser, and this is another laser. And then there's the vacuum chamber where you use, electric fields to guide vacuum ions across the chamber. And then you use laser to interact with them to see how the spectrum and the internal electronic structures and the energy levels of molecule look like. So those are fantastic. But like in the second year, I realized, it seems like I'd like to do theory better. So at that time, Professor Bernard Rubinstein just joined Brown in the same year. So I end up switching to focus more on theory side for my research. And so the research focus is mostly studying developing classical algorithms. One flavor of that is called quantum Monte Carlo algorithm to study quantum systems. So these quantum systems are mostly interacting electrons in molecules and solids. So it looks like, I would be happy to just be, starting to do theoretical research and write this long thesis, which composed of 2 parts and an awkward name because I really don't know how to unify them. So the first part is about classical algorithms on electronic structure theory. And the second part is more on the experimental side, collaborations on spectroscopy side. But that's not the sort of the end of the graduate school. So the reason is that because of Moore's law. So when I was, playing around with classical computers and developed this fantastic quantum Monte Carlo algorithms to study electronic structure quantum systems, so I realized how fantastic classical computers are. But unfortunately, we all probably see this plot, as a function of time goes on, where the computers we're using now is steadily, exponentially growing in terms of densities of transistors or the computing powers. But it seems like by the end of 2020 or in the time of my graduate school, there's news floating around saying, okay, we are hitting limits on classical computers. And then because we cannot pack enough, transistors to make transistors small enough on the small computers. And then there's going to be a harsh limit on the computing power of classical computers. That seems to be a warning sign for me, to think, okay, maybe, if the computers is not advancing, then we have limited room in improving on classical algorithms to study chemistry. So I began to think, okay, computers are really fantastic. We start from materials like doped silicons, and then we make this small nanometer size of transistors, and then we make them, integrate them all together to perform a lot of computation tasks. So really by this Moore's law, it's hard to shrink the size of the transistors further. Is really just saying, the gate, this is the metal gate, the width of the gate is roughly just sub-nanometers. And it's really hard to shrink them further because you will run into quantum effect, and then there's a lot of heating effect engineering challenges. So I got tricked by this idea of, okay, if classical computers are really amazing, why can't we make molecules into computers? Because the naive thought is that, okay, molecules are super small, but then you can almost synthesize any molecules you like. And then why not take a molecule which is angstrom size and then try to make them into smaller transistors? So that was like the basic simple question that tricked me of thinking more along this direction. So in the second and third year of my graduate school, I take a little bit of detour to spend half of the time studying more on classical, electrical and computer engineering. Really, what I want to learn is how on earth was, people able to really build computers from semiconductors. So with the aim of learning how to, or think more about how to use molecules to use them as computers. And then, I did a master's degree via this open graduate education program at Brown, which is very nice and supportive, for the education. So, by the end of my third year, well, I certainly learned a lot in the program, but I still don't yet know how to make molecules into computers. But I think that's just a long-term problem and challenge in the field that is still interesting to think even now. So in my fourth and fifth year, I kind of fully back to research on quantum chemistry and I continue the research on classical algorithms for electronic structure theory. And then I graduate. But during the time of my graduation, I realized that this question of how to make molecules to do computation, the hard part of it is really to study quantum properties or how to use quantum properties of molecules, how to manipulate them, how to control them. So this is essentially the field of how quantum computer emerged, basically use quantum system to do computation. So I decided to take a deep dive into the quantum side of the quantum system. So, that's where I end up right now, as a postdoc in MIT, studying a lot about quantum information science and the chemical physics and quantum chemistry. So I guess, in the final year of my PhD, I also started to read a little bit about this famous textbook in quantum information science by Ike and Michael Nelson. So that's basically, I think, my trajectories, from undergrad to postdoc right now into quantum. So it's not a smooth trajectory where I start from, the hardcore of quantum computation. So I kind of start from physics side and then back to chemistry and then detoured a little bit to engineering side. And then now, decided to study more deeply about the core of quantum information science. So that's, basically the trajectory, how, my trajectory look like. So if there are any questions at any time, feel free to interrupt me. So don't have to wait till the end. So with that, I wanted to give you kind of an overview of the kind of research I'm interested in right now. As Troy mentioned, I mainly study quantum mechanics, and it's really in the intersection of quantum information science and theoretical and the chemical physics. So in the one side of the research, I'm interested in how to use the law of quantum mechanics to do computation, as I mentioned previously. So I work a lot on quantum algorithm development. So these algorithms are the core part of how to leverage quantum computers to perform useful computations. One of the recent research we did is to use the quantum singular value transformation algorithm to develop a fully coherent quantum dynamic simulation algorithm for simulating electronic dynamics and the spin dynamics. But of course, quantum mechanical systems are usually dissipative. So on that front, I'm also interested in different kind of error correction schemes to combat this kind of dissipation on quantum systems. So one of the recent work is to think about other coarse-grained version of error correction schemes that can happen at the level of algorithms instead of at the lower level of gates and quantum states. Beside from the fundamental side of algorithms, I'm interested in applying this algorithm to study properties of quantum systems. And the most interesting quantum systems for me are electronic structure systems, because electrons are interacting and they are super hard to simulate on classical computers. So the work I'm going to focus on the later part of the talk today is to leverage small quantum computers to solve large electronic structure problems. And then there is some other previous work, as I mentioned during my PhD, of using classical algorithm to study, electronics behavior at considering their thermal properties at a finite temperature. So we have some work on studying molecules and also algorithms generalization to solid state materials. But beside electronic, we all know that there's another kind of quantized degrees of freedom in nature, which is vibration, or you can call it, bosonic degrees of freedom. So if you think about these bosonic oscillators, they might appear as vibrations of molecules, like the bound stretchings, or they might appear in materials as, phonons, where the atoms are just vibrating near their equilibrium positions. Also, if you put, a very small confined region and put some photons into it, there might be, standing waves where the photons are quantized. So there's another scenario where, quantum optics might be relevant for bosonic degrees of freedom. So this kind of quantum system is additional useful quantum resources to be used for computation. So in that sense, I'm interested to study, how can we leverage this kind of continuous variable oscillators, bosonic systems for computation and sensing tasks. We have some recent works on, constructing a multi-dimensional qubit systems for computation from a single oscillators. And then there is some ongoing work of studying how to hybrid this qubit and the bosonic systems for general task quantum computations. And then the last part, of course, is the connection to chemical physics, where I was doing a lot of, collaboration with experimentalists studying this kind of weakly bound electronic states in molecules. So they are super diffuse in the sense that their size are like nanometer scale. So if you heard about Rydberg atoms, these are kind of like the analog of Rydberg states in molecules, which share similar properties, but are also very different. So I'm interested in see how this kind of platforms or states can be used for useful, quantum information processing tasks. So overall, I hope, the theoretical algorithms and protocols developed can be efficient to simulate systems and also scalable for large scale systems, as well. This has to be robust against noise.
Jan?
Yes.
We have one questions comment in the chat from Yan Wong related to the dissipative component that you described. He asks, do you mean non-unitary or no energy conservation?
Yeah, so both. So when you have dissipation on the system, of course, the time evolution will be non-unitary. But energy conservation, violation of energy conservation is a special kind of, dissipation where you have amplitude damping, where you change the energy of the system with the environment or whatever. But in addition to, energy non-conserved, there is another kind of dissipation where you just change the phase, of your quantum states. These are called, phase damping or phase noise. So by dissipation, I mean in general, this kind of both noise in quantum systems.
Okay, thank you so much.
All right, so let me continue. So that was, the most of the first part. So now I'm going to focus a little bit more on research side and tell you a little bit about, the concrete research problems. So I just want to give you a general overview of the kind of chemical physics problems that's kind of interesting. What kind of processes are we interested in terms of chemistry, and how can physical laws be used to study chemistry? So we might be interested, in studying condensed phase chemistry, where this plot is showing a solution, a sodium chloride crystal, how that gradually dissolves into a bulk of water, solutions. And then people are in general interested in how the microscopic solution process happens, how one atom or one ion of the sodium or chloride dissolves gradually into the bulk water. So this can be useful. The law of statistical mechanics can be super useful here. And then when we talk about quantum properties of chemical systems, of course, we have electrons, we have other kind of quantized degrees of freedom. So this is the field of quantum chemistry. And then if we try to probe, systems like molecules or materials, we need to use some external field or light or laser as you wish. Now, this is more or less the light matter interaction field where spectroscopy is very useful. So let me delve a little bit into quantum chemistry side and electronic structure theory. So one of the very interesting problems in chemistry is really to predict the chemical reaction or complex chemical reactions in realistic environment. So I think that seems to be the end goal of doing all of this theory. But here I'm showing you, very not so complicated organic molecule, where there might be, this hydrogen proton transfer from one small molecule to a giant big molecule. There might also be electron transfer in the jump from one side to the other side. And oftentimes, this proton and electron can couple together. So this kind of a reaction is one of the most difficult reactions to predict in theoretical chemistry, but it also happens a lot in different, scenarios. Now, there might be different mechanisms. You might think that the two couples together to transfer, or they just, one of them electron transfer first, and then proton got transferred to a different place. So these microscopic mechanisms are kind of hard to nail down from a theoretical point of view. Another kind of process we are interested in chemistry are ultra-fast dynamics of electronic redistributions. So this is one experimental work that's performed where the authors ionize one electron from these organic molecules. And then it turns out that in a 5 femtosecond time scale, this ionized electron will create a hole. This hole will quickly redistribute it across the entire molecule. And then this is also, you can think of it as where a chemical reaction happens, then the rest of the molecule electron is going to reorganize. So that also changed the property of the molecule significantly. So if I think about all kind of different degrees of freedom, in molecules or in chemistry, we see electron motion, right? And then we see nuclei motion, where this hydrogen might be transferring or other atoms might be moving. And then they can couple together. And electron and nuclei also have spins, which are different kind of quantum mechanical property. And in a realistic environment, there is solvent effect, like the water molecules or other organic solvents around these reactions. That's going to make things very nasty and complicated. One of the things from a theoretical point of view, to make progress, we make assumptions or do approximations. So one of the key assumptions, I think, in quantum chemistry is to keep nuclei frozen and then just to focus on the electrons. So this helps to reduce the degrees of freedom a lot, but also because the mass of nuclei and electrons differs by roughly 2000. So this separation is usually justified in most of the cases, but it fails in cases like this kind of proton light mass transfer that I mentioned. So with this assumption, then we can just focus on electrons and then study what their ground state wave functions look like, and then or excited states or finite temperature states. And the hope is that this simplification will make things simpler. But it turns out that it's not even that simple, even if you only look at electrons. So I will give you some intuition about why that's the case. So if I just see any objects, right, I zoom in a lot of times, what I see is these atoms arranged and there's electrons serves as chemical bound. In an isolated case where if there's no adjacent atoms around, there's only one isolated atom, then the shape of the wave function we all know roughly look like S-type, P-type, or D-type. It's very regular. What makes things difficult is when you combine or put two atoms together very close nearby, and then there is electron is going to have interactions between them. The wave function is going to overlap. So that's what makes things more difficult. And then the core of electronic structure theory is to figure out when you put a lot of the atoms and the electrons together, when they all interact, how their wave functions look like. And then from that, we can actually defer or induce a lot of useful properties. For example, again, take silicon as an example. If we study their free energies, basically some kind of energy order at finite temperature. So whether they are in, let's say, different structures of alpha cores or beta cores is determined by the energy order they have. And usually this kind of different structures lead to different properties of the materials. We might also think about studying not only ground state, but also excited states. Then in materials, we might study, okay, how much energy do I need to promote one electron from the ground state to the first excited states? So this determines the excitation gap, which is closely related to a lot of different spectroscopy information and optical response properties. And then lastly, by mapping the energy of the system as a function of nuclei coordinates, you might get something called a potential energy surface or potential energy curve. And then this curve and the crossing of them, energy order and the derivatives of them usually dictates how electron transfer. And then by combining with chemical reaction rate theory, we can try to compute, or predict roughly what the rate of reaction is. So this is very useful. But if I really think about how do I tackle electronic structure theory, it's not easy at all. In a real molecule, there's going to be a lot of orbitals. Let me just try to count how many electrons or possible configurations are there in a single orbital. So because electrons are fermions, so this orbital might be empty, or it can be a spin up electron or a spin down electron, or it might just be occupying a spin up and down electron. So in one orbital, there's usually 4 cases. When we have let's say hundreds of orbitals, then by naive counting, the configurations we have to consider is just going to be exponentially large as the number of orbitals or electrons increase. So that's going to be really difficult to study. Usually, the philosophy of making progress with this difficult problem is to try to select useful or important configurations from all of this exponentially large Hilbert space or dimensions. But if you think about the whole entire range of chemical reaction happens, actually a lot of this configuration or almost all of them can matter. So across all the range of reactions, it's really hard to narrow down, which part is important, which configurations are not important. To give you just a rough idea of what the numbers grows. So I'm taking a very simple example of a molecule composed of 8 hydrogen atoms. And I can use different level of different number of orbitals or discretization to study these molecules. So these are the standard, number of orbital sets, which is called basis set in theoretical chemistry. So the numbers in the parentheses are just the number of orbitals I have. Now, if I count the number of configurations, as I was trying to do here, you can see that it grows very fast. So that's kind of very hard to do. Classically, as I mentioned, we usually try to select important configurations. 2 of the high-level philosophy we're doing this is one of them is doing truncation, and then the other is try to do sampling. So truncation means you throw away some configuration. Sampling means, okay, let's not try to completely throw all of them away. Try to sample all of them, but just by using a probability distribution to see if any one of them is more important than the other. So we kind of trying to include the important ones better than the unimportant ones. But as I mentioned, there is harsh limit on where what kind of regime this kind of methods works or this approximation works. So it seems like what we need for classical computers is really an exponentially large classical computer size to study all of these chemical problems exactly. So that's going to be very challenging. So I want to give you this plot of given this problem in the past half a century, there has been tremendous progress just on the leveraging classical computers to solve theoretical chemistry problems. So this is a tree from a textbook of quantum chemistry, which trying to summarize, a lot of the state of the art in the field of quantum chemistry. As you can see that on the bottom of the tree, these are mostly the basic assumptions of quantum mechanics. After all, we're using quantum mechanics to study, electronic motions, as Paul Dirac put a long time ago. Now, as the tree grows, there is more, subtleties and approximations and branches of the tree that turns out to play a lot of different roles. So I want to highlight, the separation of the nuclei and electron I mentioned, roughly located here, which we often call the adiabatic approximation. Now, if you make this approximation, on the one hand, then you can study how just the nuclei motion, right? So these are the molecular dynamics, simulation, all that. Now, if you focus instead on electrons, then we can study a lot of the electronic structure problems. And to studying electronic structure problems, the first thing we do is to discretize the continuous space. As I mentioned, different levels of basis set in the last slides for the hydrogen 8 molecule. So people develop different kind of basis set that's turn out to be very simple to deal with theoretically on classical computers. Now, with this basis set, we are ready to write down the Hamiltonian and then do very simple approximations. So one of the core approximations in quantum chemistry is called Hartree-Fock approximation, which basically ignores the interaction between electrons, just to treat the rest of the electron as mean field for the electron you're interested. And then this forms almost the basis of all much better electronic structure theories as laid out in this branch, where there are density functional theory, there are couple cluster theory, there is a configuration interaction or many-body perturbation theory. So those are more costly but more correlated, accurate electronic structure theory. But every one of them are still, approximate, because as we mentioned, it's really hard just to treat, electronic structure on classical computers exactly. With this theories developed, then people can, seek a lot of, I guess, applications, right? So here on the corner of the tree, you see chemical reactions, and then there's other electron transfer theories and all that. That's basically, I think, summarized in a very good amount, how classical computers works for quantum chemistry. But now with the invention of quantum computers, it seems like the structure of the tree is going to be changed. And we don't yet know, or we're just starting to know, how quantum computers can play a role in solving a different kind of chemical problems. And so now, in the next few slides, I will give you a high-level, overview of how quantum computers can be useful to just speed up things a little bit. So we know that, just intuitively, to study quantum mechanical systems, we might just as well build, computers out of quantum mechanical systems. Well, we are interested in molecules. Why not we just try to build, let's say, computers out of molecules, like I was thinking during graduate school. But it turns out that it's really hard because molecules are complicated and they lack controllability. To really make computations, it's like you have to make very precise controls on the quantum system. So the approach then people take is we can simplify this stuff a little bit. Let's not worry about a lot of large quantum systems. See if we can just isolate 2 levels of any quantum system out, and then see if we can control only 2 levels to a very high precision to perform computations. As you might know, these 2 levels are called qubits, right? And then we developed a lot of theories on how to control qubits, and then we can concatenate many of these qubits together, and then try to do some operations between qubits to perform computation. And then the goal is to, can we map our chemical problems into this quantum computers, so-called, in a simple controllable fashion of quantum systems. And then we do some operations on the state of the system. This operation is denoted by a unitary operator U. And then in the end, we do some measurement on the qubits to collapse the information from quantum to classical to tell us, the result of the computation, or tell us something about the molecule we're interested. So if you look at the whole, workflow here, this is basically how usually we do computation, quantum computation. So quantum algorithm designs focus on, the last two parts. Basically, how do we best come up with this operation U and measurement such that we get useful information we want. And this U really manipulate the probability amplitudes, or this, complex coefficients in front of each one of the quantum states, and they can be in superposition. And then the power of a quantum computer really lies at how people think carefully about how to manipulate these amplitudes. I would just say there are other kind of quantum computing scheme exist, such as measurement-based quantum computation, but I will just mention it and not delve into detail. So I will give you a very simple intuition of how quantum speed up as compared to classical can be possible just by manipulating the amplitudes. So in this simple scenario, there is one thing I can do to the amplitudes is trying to amplify the amplitudes, make it bigger. So I want to first introduce something called a quantum circuit. Let me just abstract away what I'm writing here at the top into simplified language people use. I have some qubits here, and I have another set of qubits here. And then the unitary operation U here is the computation I design. Let's say in the end, I need to measure one qubit and then obtain some useful wave functions on the bottom qubits. So this whole thing is called a quantum circuit, and time flows from left to right. So as time goes on, the computation goes on. That's basically one way of looking at this diagram. So what I say in this scenario is that only when my measurement of the upper qubit is 0, then I get some useful wave function in the bottom register. If that measurement is 1, I get some rubbish here. So I don't want that. And oftentimes of the case in quantum computation, when we do such measurement, so the measurement probability of getting the useful result 0 is not that large. It's just some finite number, real number a squared, let's say. This is the probability. In this scenario, let me assume, a is really, really small, like much smaller than 1. Now, if I just run this computation once and measure, I might fail, right? I might get some rubbish here because I measure 1. So how do I get useful information? So, okay, naively, I can just repeat this computation 3 times, right? So I can probably get something like 3 times this, this probability. So that's not surprising. As classically, I repeat something 3 times, okay, I got 3 times the success probability. But it turns out that in quantum computation, if you really try to coherently manipulate these amplitudes, you can again use just the U 3 times here, interleaved by simple qubit operations without doing measurement. So the only measurement you do is in the end of the circuit, and then by consuming again 3 U here. And then what you can achieve is that you can amplify this amplitude A directly by 3 times. And then in the end, the measurement outcome of being 0 in the qubit, getting some useful computation, is actually 3 squared, 9 times the original success probability. So if you compare 9 to 3, that's like a quadratic speed up. So you can perform the same argument of saying that for any constant C, right, it can always give you a C squared boost in success probability. So that's the most naive, version of how do I understand the power of manipulating amplitudes. So you might think square root speed up is not that severe, but for people with a quantum chemistry background, so this speed up is really is something like you're getting couple cluster singles and doubles calculation with only Hartree-Fock cost. So if we know that couple cluster singles and doubles are the gold standard for quantum chemistry, then this speed up is actually not that bad. It's actually a very good speed up. And the good thing is that quadratic speed up is always guaranteed in quantum computation. But oftentimes we can aim for higher, speed up, or polynomial or exponential speed up. There is a classical analogy of this speedup, which I will skip for now, but I can come back to this later if people are more interested. But it turns out that we can do much better than only amplify the amplitude. We can actually do any nonlinear transformation in the amplitude. So there is this recent work of a new kind of quantum algorithm called quantum singular value transformation, which built on previous work of quantum signal processing that give a unified framework of how to constructively transform any quantum amplitude in a nonlinear fashion. So let me just walk you quickly through how this works. So let's suppose I have, some general amplitudes A here. That's part of the unitary. By combining with some single qubit operations, I can actually realize, a polynomial transformation of this amplitude A. So this polynomial, of course, can be high order. And then the overall quantum circuit looks like very simple, just repeatedly applying, this W, which have the amplitude you want to manipulate. And then you just combine that with some single qubit operations. So the degree of the polynomial roughly proportional to the depth of this circuit. So in the amplitude amplification case, where we see that, this polynomial is just a special case of a linear function, multiply some constant 2a. But you can also think of the dynamic evolution problem, which people often call Hamiltonian simulation, as just figuring out some polynomial approximation to the complex exponential e to the iht, where you map Hamiltonian h to a unitary operator. So there can be, much more generalization or different ways of framing other kind of computations in this framework. So with that, as I mentioned, we can actually simulate, dynamic evolution, charge oscillation in chemical molecules. This is a very simple case of hydrogen 2 molecules of femtosecond dynamics simulation. And then this is the error correction work I mentioned before. But we know that, okay, everything seems to be so good so far, but making large-scale quantum computers is actually very difficult. So if we think about earlier realizations of NMR quantum computing and trapped ion or superconducting systems, there is always going to be quantum noise. As a result, right now we are in the era of NISQ, called noisy intermediate scale quantum era, where there's a lot of noise on quantum systems, and we cannot run very deep depth quantum circuit. And as a result, we always have this kind of shallow quantum circuit and then have some measurement and then feed back this measurement classically to this quantum circuit. And then this is called, variational quantum algorithms, or one version of that is eigensolvers. And that's the dominant, quantum algorithm right now. But it turns out that theoretically, it's actually possible to build a large-scale quantum computer because error correction is possible. What that says is that we can actually correct errors or noise in quantum systems faster than they are accumulated as you grow the computers larger and larger. So then there are a lot of companies trying to build, let's say, large-scale quantum computers which are fault tolerant, which basically means there is no error. But as you can see that a lot of this roadmaps in the near future, there's going to be quite small quantum computers, although they are error corrected. So if we think about the problems we're interested, this kind of large chemical problems or materials that we're interested. But on the other hand, we might also just have very small quantum computers. So there is a dilemma here. How do we use small quantum computers to solve these large problems? How do we move forward? So one idea is, okay, we might think about parallelize a lot of quantum computers to link them together and then study a large problem. So there is some work in computer science and also in C2QA that a lot of different groups are interested. So in this work I'm going to present today, we take an opposite approach of trying to break the original large system into smaller fragments and then study each fragment using a small quantum computer and then link the fragment solutions together afterwards. So to give you some idea about how quantum embedding, so this general idea of split large system into fragments are a field called quantum embedding. So the idea goes as follows. Suppose I have a any quantum system, let's say two-dimensional systems. Oftentimes the interactions have localities, and also the quantum entanglement between a subsystem and the rest of the site have locality. So the amount of entanglement that's going to be mostly focused, concentrated, is going to be on the boundary of the fragment. And then the site that's super far from this fragment are going to have very small entanglement. So what we can do is try to break the system into smaller size. And then we can then use simulate each one of the different colors of subsystem, and then try to stitch them all together. So this kind of idea leads to a lot of interesting development in the quantum chemistry community in the classical computer side, where you can do quantum embedding. So, but there is some limitations of doing embedding on classical computers. I will give you one example of classical bootstrap embedding on classical computers to see how this works and what are some of the limitations. So we start usually from fragmentation of the system, as I mentioned here. You break the system into smaller pieces, and then you can choose, in this special case, a bootstrap embedding. We choose overlapping pieces. The reason is that, as I mentioned, the entanglement mostly on the boundary. So the edge side in one fragment is going to be described in much worse case than the center side. So as a result, we can use the better description on the center sides to improve the worse description of the edge side on different fragments. So by matching, the edge side to the center side, we can hope to improve the description of the fragment iteratively. After the fragmentation, then we use, classical computers to deal with each fragment, and then we try to stitch, the fragment solutions together on classical computers. This is performed by stitching local observables or simple observables that's easily computable on classical computers. And then we generate some classical potentials to modify the Hamiltonian of each fragment. And then we solve the new Hamiltonian, and this cycle goes along. So these are some kind of optimization cycle we can build and use classical computers to iteratively improve the solution of fragments. So two simple facts are: the larger the fragment, the better the solution, and then the larger the overlapping region, the better. But there are challenges of doing classical bootstrap embedding. So one of them is because classical eigensolvers, as I mentioned before, oftentimes approximate. It's really hard to do exact eigensolvers because that requires exponential large of spaces. And the second part is that this classical matching part only matches one very simple local observables. But in principle, one should try to match the full many-body quantum observables on the overlapping side. So this one RDM means one particle reduced density matrix. So we might be thinking that matching full reduced density matrix is actually a better solution. And then these errors might accumulate as one goes the iteration. So what quantum computers are good at is, as I mentioned, the eigensolver can be changed into a quantum eigensolver, which can realize, a quasi-exponential speed up in terms of getting exact solutions for the fragments. So here it's a plot of showing how the runtime of the quantum eigensolvers scale as a system size. You can see that the quantum eigensolver scales roughly polynomially, but then the classical eigensolver runtime scales exponentially. So the second part, what quantum can, yes.
Jan?
Yes.
We have less than 10 minutes, so
Great.
Maybe we can bring this portion to a close to allow some time for.
Yes, let me just wrap this part.
Sure. Yeah, I think this
quickly.
is a good place to transition.
Yep. So the second challenge I mentioned is, local observables are matched on classical computers, but in principle, you want to match many-body observables. So it turns out that quantum computers can achieve this by a simple modification of a quantum circuit called a swap test that can just do the matching of all the many-body observables simultaneously. So based on this, we develop a quantum algorithm that overcomes the limitations on classical quantum embedding theory. and achieve quadratic speedup, for simulating electronic structure theories. So I will stop here. So if you are interested, we have a archive preprint paper that's put up in the end. Let me just skip all of this and point you to the papers here. And I want to thank the authors, on this paper, especially Professor Troy Van Boris for this work on the chemistry side. And I want to thank you for your attention. So maybe we can happy to take some questions here.
So we have a question in the chat, and it's from Manas. Manas, are you able to maybe summarize the question in a succinct manner that you posed in the chat?
Sure.
Manas?
Sure. So I actually have two questions. And the first is, all flavors of actually single value transforms requires a block encoding of the initial Hermitian operator. Now, is this block encoding always efficient, even if your Hermitian operator is not sparse? By efficient, I mean, and this always be done in actually poly-n gate?
No, in general, it's hard for any arbitrary Hamiltonian. But for simple Hamiltonians, it can be simple or useful. But I think this is still some ongoing research. People are trying to think how to actually block encode quantum chemistry or electronic structure Hamiltonians into a unitary operator. And then it's interesting, and there is some libraries and recent work on how to do this. We also thought about a little bit about this problem, but it's still, I think, an pretty much open question for now.
Okay. Are there any other questions? Excellent presentation, and we need to bring you back for the second part at some point, but really exciting work. Any other questions right now?
There's also a second question which I had.
Okay. There is a...
Yes.
Okay.
Yes. So this is about amplitude amplification. So in the naive Gruber search, you can overshoot, but then there are advanced version of search that is fixed point, means that guarantees you will not overshoot. When you are close to 1, the amplitude are close to 1, you can guarantee that, you always stay very close to 1. And then there's a formulation of this in terms of QSVT that guarantees the fixed point property by choosing the phase angles carefully.
I see. Thank you so much. Thank you.
I did have a question for you. Can you what would be your definition of a high fidelity small quantum computer?
Right. So in
today's space where we are now.
Yeah. So by that I mean that we need to reduce the gate error below the error correction threshold, such that we can apply some error correcting code to make the quantum computers fully fault tolerant. So we might have, let's say, 20, 30 qubits, but then those has to be perfect logical qubits.
Yes.
And then we can do arbitrarily long quantum computation with it, or rather a very long quantum computation within the coherence time of the system, of course. With that, then a lot of this embedding idea can be nicely applied, because as the quantum circuit we come up with actually is very deep depth. Although we shrink the use of number of qubits, but then we do need very deep quantum circuits to actually make this work. So I think that's something one direction of fault tolerant small quantum computers can be useful.
Okay. And so the systems that you guys are using at MIT, I'm just curious about, are you using a particular hardware platform, or are you guys building in-house systems? What are you using to?
Yeah, so in this work, these are classical simulations of quantum algorithms. We haven't run it on any quantum device.
So, you haven't gotten to that.
Yeah, but that's a nice question and direction to look into.
Okay. Any additional questions?
Yes, I have additional question.
Go ahead, please.
Yeah, I want to ask that according in a chemical reaction, I want to ask that how the we say that nucleophile attacks on a species. How do you explain physically that these attacks, these lone pair attacks? How do we explain these physically?
Sorry, can you say the question a little bit more? The lone pair, how do I think of a lone pair physically, or?
Yes, for example, in reactions, we say that lone pair attacks on a given species. How do we see that on a magnified scale? Or you can say how the lone pair attacks or this nucleophile attacks on other species.
Right. So I think the physical process, how I understand that is that, you have some part of the molecule that's more positively charged, and then that's attractive to some negative charged electron, right? So then you attract that electron over, and then that's what you call electrophilic. But then you can have the opposite, where this part might be negatively charged, and then it trying to attract this positively charged nuclei. That's nucleophilic. So those are, chemical reaction way terms that people think about this. But on a theoretical level, what I always think about that is I can always write a Hamiltonian down that describe this interaction theoretically. And then I can try to then describe what a dynamic process evolution as this attack happens, right? How electron moves closer, how the nuclei positive charged part moves closer. So that's by mean dynamic simulation, I mean quantum computer has the power of simulating that kind of reaction dynamics directly. Although that's fast, the Hamiltonian might be difficult, but it's possible.
I got you. Thank you.
Okay, I think we're down to our last minute. Jan, you have any parting words of encouragement to our undergraduates who are in our audience who are looking for a career? What words of advice you can give to them?
Right. So let me just pull up, this slides again a little bit. We're in a very exciting, area or range or era. So we are trying to branch or modifying the tree of quantum chemistry by leveraging the power of quantum computers. You can imagine that, let's say in half a decade, how the structure of this tree is going to change. It is imaginable. It's hard to imagine, but it's exciting and interesting to think and work towards that. We are beginning to think along that. And last sort of piece of advice, I think from my trajectory is that, you see my trajectory of getting into quantum is a little bit convolved. But I always try to, ask questions like follow whatever I want to do or I was trying to do, although it's going to be hard. But I think I learned a lot from this trajectory, and I encourage you all to ask yourself this kind of questions and see, go whatever direction you want to go and then pursue the kind of stuff you want to do.
And Troy, for those undergraduates who wants to come to walk down the infinite corridor to your office, how do they get to you? What opportunities there are?
Well, I mean, yeah. Well, JetBlue may still need to be involved to physically get them here, but I think, Raymond, one of the things that's nice about the things that Yuan is working on is that once you start taking quantum computing and using it to solve problems, there are certainly situations. I mean, quantum computing, all the new algorithms, it's very hard to get all of it into your brain at once. It's even hard for me to do so. So I can only imagine for undergrads how overwhelming it can seem. But I will say that once you start talking about actual calculations, solving actual problems, there is a sense in which you can learn while doing with some of these things of saying, okay, well, here's a problem you want to solve. Let's try to learn how this algorithm works while we're running the calculations to solve the particular problem.
Sure.
And that's certainly one of the MIT mottos, is that you learn while doing it. So.
Okay. Excellent. Well, thank you all for joining us today. This is a really phenomenal kickoff. Jan, you did a fabulous job. Troy, thank you for being with us. Thank you all. We are back again in 2 weeks. Is that right, Kim? We're in 2 weeks, same time,
That
same
is
place.
correct. Yes.
And really invite your friends and please join us. And we thank you all. So thank you.
Thanks, everyone.
Thank
Bye-bye.
you.